So we've had various examples where we prove that 2 points can be connected by a path. But we also want some tools to be able to prove that 2 points cannot be connected by a path. So we're going to have a couple of results like that just now. So start with this one. So suppose we've got a continuous map. And we're going to suppose it's never zero. In other words, f of x is not equal to naught for all x and x. And let's suppose that we've got points A and B in x. F of A is negative and f of B positive. Or it could be the other way around, but this will do. Then I want to claim that A is not equivalent to B with respect to this equivalence relation that we've been considering. So let's just spell that out. Saying that there's no path U from A to B in X. And the proof is not very hard. And the key point is the intermediate value theorem. So we're going to suppose for a contradiction that some such path U exists. So that means that U is a continuous map from the unit interval to X. U of 0 is A, U of 1 is B. Okay. Then because the composite of continuous maps is continuous, we see that the F composed with U is giving us a continuous map from the unit interval to the reals. The value at 0, of course, is f of A less than 0, and F composed with U at 1, that's f of B greater than 0. So now the intermediate value theorem says there's some number t in the unit interval such that F composed with U at t is equal to 0. In other words, the point x, which is define x to be U of t, that has f of x. So this is a point in x, obviously. So this has f of x equals 0, contrary to assumption. And this was part of our assumptions here that f was supposed to be a continuous map that's never 0. Okay, so that so this proves that there can't be such a path. Okay, so we can have a little corollary of that. Okay, let's suppose that X can be written as a union of two sets U and V. Where U and V are both open, and assume that U intersect V is empty. Okay, so X is the disjoint union of two open sets U and V. Now suppose we've got some point A and U and some point B and V, and I want to claim that A cannot be connected to B. And so we're just going to reduce this to the previous statement by concocting a suitable function f. So we define our function f like this. It's going to be -1 for points in U and +1 for points in V. And so can't be any collision between these two clauses because U intersect V is empty, and U union V is all of X. So always one or the other clause applies. So this gives us a well-defined map from X to the rings. So I want to claim it's continuous. And remember what that means. In other words, the pre-image of any subset, open subset A of the reals is going to be open in X. But it's easy to see what F inverse A is. So most obvious case, if both 1 and -1 lie in A, then F inverse of A is going to be the whole space X. If -1's in A and 1 isn't, then F inverse A is going to be U. F inverse A is V. If -1 is not in A and 1 is in A, and F inverse A empty if neither 1 nor -1 lies in A, and it's open in all cases. And now if A is in U and B is in V, then F of A less than 0, which is less than F of B. So A is not connected to B by the previous proposition. So that's a useful result for proving that 2 points cannot be connected by a path. So as an example, let's just consider X being the integers. Okay. So claim that if A and B are integers which are different, well, let's suppose that A is less than B, simplicity, then A and B cannot be connected by a path. So in particular, we can just define a function f from Z to R by f of x, say, is x minus b plus a half. That's continuous with f of a less than 0, less than f of b, and f is never 0 on z, because for it to be 0, x would have to be equal to b minus a half, but b minus a half is not an integer, so that can't happen. And so by the proposition that we proved a minute ago, you've got a continuous function, positive at b and negative at a, so they can't be connected. Continuous, never 0 function. Another example. So we've considered this space, remember, GL2R. That's a set of 2 by 2 invertible matrices. And so we've got this determinant map from GL2R to the reals. So that's continuous and it's never 0, right? Because matrix is invertible precisely if its determinant is non-zero. So this is a never 0 function. And we can define I to be the identity matrix and J to be the same thing, sort of flipped around like that. So these are both invertible matrices. The determinant of I, of course, is +1. The determinant of J is -1. So I cannot be connected to J in GL2R. And just extending that story a little bit, if we just put U instead of A, such that det A is positive, and V is a set of A, such that det A is negative. Okay, then you can check that these are actually both connected. So I won't really recall the proof here, but we studied this example, this space in a different example. You could actually come up with a specific homeomorphism of the whole of GL2R with R3 cross S1 cross S0. And so individually, the positive and negative parts are both homeomorphic to R3 cross S1. And that's path connected. And using this, you're going to see. Can't see that. Okay, so I'll just say it. So you can check that the pi0 of GL2R, the set of connected components, well, U and V are they're both each connected components, and they're the only two connected components. So pi0 GL2R is just going to be the set U, V, which has size 2.